모두 착석해 주시기 바랍니다. 아울러 소지하고 계신 휴대전화는 진동이나 무음으로 전환해 주시면 감사하겠습니다. 다시 한번 안내 말씀드립니다. 잠시 후 대한수학회 창립 80주년 기념 국제학술대회 개회식이 시작될 예정입니다. 아직 착석하지 않은 참가자 여러분께서는 장내로 입장하셔서 자리를 정돈해 주시면 감사하겠습니다. 다시 한번 안내 말씀드립니다. 잠시 후 대한수학회 창립 80주년 기념 국제학회 개회식이 시작될 예정입니다. 아직 착석하지 않으신 참석자 여러분께서는 장내로 입장하셔서 자리를 정돈해 주시면 감사하겠습니다.
안녕하세요. 저 혹시 빈자리에 짐 올려놓으신 분들은 바닥으로 내려주셔서
안내 말씀드립니다. 오늘 개회식은 주요 내빈 여러분께서 입장이 완료되는 대로 곧 시작할 예정입니다. 참석자 여러분께서는 좌석에 앉아 잠시만 기다려 주시면 감사하겠습니다. 안녕하십니까. 대한수학회 창립 80주년 기념 국제학술대회 개회식 사회를 맡은 한강진입니다. 오늘 이 뜻깊은 자리를 함께해 주신 국내외 귀인 여러분과 수학자 동료 여러분께 깊은 감사의 말씀을 드립니다. 지난 1946년 창립 이래 대한민국 과학기술의 든든한 기반이 된 대한수학회는 그 80년의 발자취를 이어받아 이번 국제학술대회를 개최하게 되었습니다. 이번 학술대회가 학회의 80주년을 다 함께 축하하는 기쁨의 장이자 서로의 학문적 지평을 넓히는 귀중한 성장의 기회가 되기를 바랍니다. 그럼 지금부터 대한수학회 창립 80주년 기념 국제학술대회 개회식을 시작하겠습니다. 첫 순서로 국민의례가 있겠습니다. 장내에 계신 모든 분께서는 잠시 자리에서 일어나 전면의 국기를 향해 서주시기 바랍니다. May I ask everyone to stand up for national ceremony, please? 국기에 대하여 경례!
나는 자랑스러운 국기 앞에 자유롭고 정의로운 대한의 무궁한 영광을 위하여 충성을 다할 것을 굳게 다짐합니다.
바로 다음 순서인 애국가 제창은 행사 일정상 생략하도록 하겠습니다. 모두 자리에 편안하게 착석해 주시기 바랍니다. 이어서 이 자리를 빛내주신 주요 내빈 여러분을 소개해 드리겠습니다. 호명되시는 내빈께서는 자리에서 잠시 일어나 주시고 참석자 여러분께서는 큰 박수로 환영해 주시기 바랍니다. 먼저 대한수학회 80주년을 축하하기 위해 귀한 발걸음 해주셨습니다. 구혁채 과학기술정보통신부 제1차관님 참석하셨습니다. 다음으로 최윤성 국가수리과학연구소 소장님 참석하셨습니다. 이화여대 이향숙 총장님 참석하셨습니다. 일본 수학계의 카주이로 이시게 회장님 참석하셨습니다. 대만 수학회의 신신카오 회장님 참석하셨습니다. 베트남 수학회의 부호앙린 회장님 참석하셨습니다. 그리고 과기정통부 기초연구진흥과 박시정 과장님 참석하셨습니다. 이외에도 많은 내빈분들이 계십니다. 근데 시간 관계상 한 분 한 분 모두 소개해드리지 못하는 점 너그러운 양해 부탁드리겠습니다. 참석해 주신 모든 분께 감사의 마음을 담아 다 함께 환영의 큰 박수 부탁드립니다. 다음은 이번 국제학술대회를 주최한 대한수학회 곽시종 회장님의 개회사가 있겠습니다. 곽시종 회장님을 연단으로 모시겠습니다.
존경하는 대한수학회 회원 여러분, 그리고 자리를 빛내주신 내외 귀빈 여러분, 안녕하십니까? 대단히 반갑습니다. 대한수학회 회장 곽시종입니다. 바로 어제가 1년 중 태양이 가장 높이 솟구치고 낮이 가장 길었던 절기 하지였습니다. 본격적인 여름이 시작되며 대지의 뜨거운 에너지가 가득 차오르는 요즘, 우리 수학회 학문적 교류에 동참하고 80주년이라는 뜻깊은 자리를 빛내주시기 위해 과학기술 컨벤션 센터를 가득 채워주신 여러분께 깊은 감사의 인사를 올립니다. 오늘 이 자리에 모인 여러분의 열정이 이번 80주년 학술대회와 축하의 자리를 한층 더 빛내주고 있습니다. 올해는 우리 학회가 해방 직후의 혼란과 척박한 환경 속에서도 고귀한 사명감과 열정으로 첫 발을 내디딘 지 80주년이 되는 해입니다. 1946년 당시 선구자들께서는 오직 수학 연구의 토대를 다지기 위해 뜻을 모으셨으며 그 위대한 시작에 참여한 회원은 단 24명 뿐이었습니다. 그러나 수많은 선악의 헌신과 회원 여러분의 적극적인 참여 그리고 애정이 모여서 창립 50주년에는 2천여 명, 70주년에는 4천여 명을 넘어 80주년인 현재에는 정회원과 학생회원 포함 5,800여 명의 회원이 함께하는 학술단체로 우뚝 섰습니다. 1946년 조선 20학회로 출발하여 1952년 대한수학회로 거듭난 이래 우리는 끊임없이 학문적 역량을 축적해 왔습니다. 그 결과 2014년 세계 수학자 대회를 성공적으로 개최하였으며 국제수학연맹 최고 등급인 5그룹에 당당히 이름을 올리면서 세계 수학계의 중심축으로 자리매김하였습니다. 이러한 위대한 성장의 발판을 마련해 주신 원로 회원님들과 지금 이 순간에도 강당과 연구실에서 정진하고 계신 회원 여러분께 깊은 존경과 감사의 인사를 올립니다. 회원 여러분, 내외 귀빈 여러분, 오늘부터 나흘간 개최되는 대한수학회 창립 80주년 기념 국제학술대회에서는 기조강연과 초청강연 그리고 대중강연을 아우르는 총 375편의 깊이 있는 학술 발표가 풍성하게 펼쳐질 것입니다. 우리 학회의 발자취를 돌아보는 기념 전시와 80년의 여정을 축하하는 기념식 등 다채로운 행사도 마련되어 있습니다. 우리 수학계의 위상을 빛낼 이번 80주년 기념 행사를 위해 수개월 동안 마음을 모아 헌신해 주신 학회 임원진과 조직위원회 그리고 사무국 직원 여러분의 노고에 진심으로 감사드립니다. 아울러 성공적인 개최를 위해 큰 힘을 보태주신 공동주관 기관인 고등과학원, 국가수리과학연구소, 서울대학교 마줄과 공간의 양자구조 연구센터, 포항공대 수리기계학습 연구센터, 강원대학교 수리과학연구소, 경북대학교 비선형동역학 수리응용센터와 후원기관인 서울대학교 수학연구소, 한국과학기술단체 총연합회에도 진심으로 감사의 말씀을 전합니다. 수학은 창의적인 아이디어와 치열한 고뇌가 하나로 연결되면서 비로소 위대한 진보를 이루어냅니다. 여러분이 오랜 시간 쌓아오신 노력과 지혜가 이번 학술대회를 통해 긴밀한 소통과 창조적 영감으로 이어지기를 진심으로 소망합니다. 오늘 이 자리가 지난 80년의 위대한 발자취를 기념하는 것을 넘어 미래 세대에게 새로운 희망을 주는 이정표가 되기를 또한 기대합니다. 우리가 공유한 학문적 가치와 열정이 다음 세대로 더 울창하게 숲을 이룰 수 있도록 대한수학회는 비옥한 토양이 되는데 모든 역량을 집중하도록 하겠습니다. 초여름의 뜨거운 열기 속에서 이 거대한 지적 교류의 장을 마음껏 누리시고 대한수학회 또 다른 미래를 향한 새로운 지평을 오늘 이 자리에서 우리 함께 힘차게 열어갑시다. 감사합니다.
예, 대한수학회의 지난 역사와 미래 비전을 담아 뜻깊은 개회사를 전해주신 곽시종 회장님께 다시 한번 큰 박수 부탁드립니다. 다음은 대한민국 과학기술정책을 이끄는 과기정통부 구혁채 제1차관님께서 축사를 준비해 주셨습니다. 연단으로 이동하실 때 따뜻한 박수로 만회해 주시길 바랍니다.
제가 드리는 말씀이 뒤에 이렇게 나오게 되는 건가요? 왜냐하면 제가 이게 축사 이 내용을 제가 약간 좀 바꿔가지고 아마 좀 제가 여기서 바로 이렇게 트랜슬레이션 할 수 없을 것 같은데 알아서 들으시기 바랍니다. 아우 많이들 오셨습니다. 저 뒤에 학생분들 막 서 계신 분들도 많은데 예 반갑습니다. 방금 소개받은 과기정통부 1차관으로 있는 구혁채라고 합니다. 저는 개인적으로 저는 이제 공과대학을 나와가지고 자연대학은 아닙니다. 공과대학을 나와가지고 이공계 그 업무를 뭐 넓게 보면 과기정책도 이공계니까요. 이렇게 한 30년 정도 하고 있는데 오늘 또 뜻깊은 대한수학회 80주년 의미 있는 이 행사에 불러주셔서 곽시정 회장님 감사드립니다. 허준희 교수님도 다시 한번 뵙게 돼서 너무 반갑습니다. 여러분 아시겠습니다만 그 80주년인데요. 아마 올해가 여러 가지 의미가 있는 해입니다. 아마 이게 대한수학회가 46년에 생길 때 그때가 서울대 경성제국대학 서울대가 이제 생겼었고요. 그래서 올해 아마 서울대도 80주년. 그다음에 여기 계신 이 과총도 올해 아마 60년인가 될 겁니다. 60년이고 뭐 정보출연연구소 여러분들 아시는 기관들 많겠지만은 뭐 키스트라고 하는 우리나라 종합연구소도 생긴 지가 이제 올해가 60년이 됩니다. 그때 많은 일들이 이제 시작이 된 것 같습니다. 내년이 되면은 내년도 의미 있는 해들이 몇 가지가 이렇게 그런 이벤트들이 있습니다. 내년이 되면은 이제 저희 과기처 지금은 과학기술정보통신부입니다만 과학기술 정책이 시작된 지가 이제 60년입니다. 그러니까 67년도에 이제 우리나라 과학기술 정책이 시작이 됐고 그때 과학기술 행정 조직이 생겼기 때문에 이제는 내년이 되면 우리 과학기술 행정도 60년이 됩니다. 이 60이라는 의미는 뭐 여러분들 잘 아시겠습니다만 이제 60갑자가 돌아가는 거잖아요. 그만큼 그간의 여러 가지 것들을 한번 되돌아보고 또 다음 60년을 바라봐야 되는 그런 전환기적 시점이 이제 있는 것 같다 이런 생각이 듭니다. 방금 전에 회장님께서도 말씀 주셨다시피 그 대한수물학회로 시작을 한 우리 수학계가 전쟁과 가난 그리고 정말 열악한 연구 환경 속에서도 수학이라는 학문의 불씨를 지켜내왔습니다. 그리고 52년 대한수학회로 새롭게 출범한 이후에 수많은 수학자들의 헌신과 노력 끝에 오늘날 전 세계가 주목하는 학문 공동체로서 성장을 해왔다고 생각을 합니다. 최윤식 초대 회장께서 학회를 만드신 이후에 그간에 많은 성과들이 있었습니다. 81년도에 국제수학연맹에 가입을 했고 5년 지났나요? 지나고 나서 20년 더 지났구나. 그 국제수학회 그룹 4로 승격이 되고 2014년에 세계 수학자 대회도 유치를 하게 되었고요. 불과 이제 몇 년 전에 2~3년 전에 우리 허준희 교수님이 또 필상을 받으시는 그런 괄목할 만한 그런 성장과 성과가 있었다 생각을 합니다. 대한수학회 80년의 역사가 곧 대한민국 과학기술의 역사이고 한국 수학이 불모지에서 출발해서 성장해온 그간의 도전과 성취의 역사라고 생각을 합니다. 뭐 수학은 저도 잘 모르지만은 수학은 과학기술의 언어라고 말씀을 늘 합니다. 단순한 계산의 기술을 넘어서 세상을 이해하는 사고의 틀이고 보이지 않는 질서를 발견하는 학문이라 생각합니다. 프랑스의 수학자 앙리 푸앙카레가 수학은 마음을 경영하는 학문이다 라고 말을 했듯이 수학은 우리에게 정확하게 생각하는 힘을 길러주고 복잡한 현상 속에서 본질을 발견할 수 있도록 하는 통찰력을 제공해 줍니다. 그리고 그 힘은 오늘날 인공지능, 양자과학기술, 첨단 바이오, 우주 등 미래 전략기술의 근간이 되고 있습니다. 저희가 AI를 이야기할 때도 또는 양자 컴퓨팅의 미래를 이야기할 때도 그 출발점에는 항상 수학적 상상력과 창의성이 자리하고 있다고 생각합니다. 그런 의미에서 수학은 모든 과학기술의 기초일 뿐 아니라 미래를 설계하는 가장 근본적인 힘이라고 저희들은 믿고 있습니다. 오늘 이 자리에서 세계 여러 나라의 수학자분들께서 함께 모여서 지식과 통찰을 나누는 국제학술대회가 며칠간 열리게 됩니다. 수학은 국경과 언어를 넘어서 인류가 공유하는 보편적 지식의 체계이기도 합니다. 수학은 국경을 모른다. 수학의 세계는 하나의 나라다라고 데이비드 힐베르트 교수께서도 말씀을 하셨는데, 이번 80주년을 기념하는 이번 국제학술 대회가 국가와 세대를 넘어 수학이라는 공통의 언어로 서로 연결하고 미래 과학기술 발전을 위한 새로운 협력과 영감을 만들어내는 뜻깊은 계기가 되기를 기대합니다. 저희 과기정통부도 연구자 중심의 기초연구를 더욱 강화를 하고 수학을 비롯한 기초과학이 흔들림 없이 발전할 수 있도록 지속적으로 지원을 하겠습니다. 혹시 여러분들 많이 들으셨는지 모르겠는데 올해 우리 지금 정부의 R&D가 전체가 35.5조입니다. 우리가 정부 예산을 한 700조로 잡을 때 35조니까 한 얼마 되려나요? 한 5%, 700조 넘으니까요. 5% 약간 안 되는데, 물론 그 중에 기초연구 예산이 35조 중에 수학을 포함한 기초연구 예산이 3.4조입니다. 그러니까 10% 정도 좀 되죠. 전체 R&D 중에. 물론 그 중에 이제 기초과학, 수물, 지화 이런 것들은 더 작겠습니다만 저희들이 그런 부분을 유심히 촘촘히 보고 있습니다. 끝으로 저는 제가 지금까지 한 30년 넘게 근무하면서 저 역시도 공대를 나왔지만 수학이라는 거를 잘 몰랐는데, 제가 대학교 2학년 때 이제 고시 공부할 때 제가 시험을 봤던 과목이 있습니다. 전자회로도 있고 전자기하게 있는데, 그걸 이제 선택을 제가 잘못해가지고 하다 보니까 그게 다 수학이더라고요. 그래가지고 이 수학을 어떻게 풀어야 되나 그랬는데, 제가 이제 뭣도 모르고 한번 수학과 과목을 들었다가 이거는 무슨 말인지 도대체 모르겠고, 옆에 있는 이제 공대 수학을 들어갔더니, 그때 이제 여기 계신 교수님들 앞에서 말씀드리긴 너무나 비약한 얘기지만은, 그때 선형대수, 라플라스 변화 이런 걸 하는데, 아니 이런 거를 왜 진작에 안 알려줬을까? 아니 이런 거를 알면은 굳이 이렇게 우리가 이렇게 어렵게 살아야 되나 하는 생각이 들 정도로, 그 수학의 이 많은 수학 영역 중에서 조그마한 부분이었던 그 리니어 알제브라, 그다음에 트랜스포메이션 이런 것들이었는데, 저한테는 너무나, 공대생 입장에서는 너무나 큰 충격이었고, 수학이 이래서 미분과 적분을 해야 되는구나, 그때 알았습니다. 저희가 오늘 80주년 셀리브레이션을 하지만 아쉽게도 우리 학생들, 여기 수학 관심 있는 분들이 많겠지만 이 건물 밖에는 많은 우리 학생들이 수학에 대한 호기심과 그런 게 좀 많이 떨어지고 있습니다. 여러 가지 문제가 있겠지만, 여기 계신 분들이, 교수님들과 여러 선생님들과 학생 연구하시는 분들께서 그 목까지 아마 좀 이렇게 같이 고민을 하고 저희들하고 풀어나가야 될 거라 생각을 합니다. 모쪼록 오늘 행사 큰 성과, 좋은 결실 있도록 기대하고, 많은 배움, 저 역시도 좀 더 이따 갈 텐데요, 많은 걸 보고 가겠습니다. 고맙습니다.
대한민국 수학계의 발전을 위해 따뜻한 격려와 지지를 보내주신 구혁재 제1차관님께 깊이 감사드립니다. 이어서 오늘 개회식에 감동을 기록하기 위한 단체 사진 촬영이 있겠습니다. 자, 무대 정리를 위해서 앞좌석에 계신 주요 내빈 여러분께서는 먼저 연단 앞으로 자리해 주시기 바랍니다. 네, 아울러 좌석에 계신 모든 참가자 여러분께서도 기념사전과 드론 촬영을 위해서 연단 위아래로 함께 모여주시면 감사하겠습니다. 네, 이것으로 대한수학회 창립 80주년 기념 국제학술대회 개회식을 모두 마치겠습니다. 잠시 장례를 정돈한 뒤 이어서 이번 학술대회 첫 번째 기조 강연이자 많은 분들이 기다리시던 프린스턴 대학교 및 고등과학원 허준희 교수님의 기조 강연이 시작될 예정입니다. 참석자 여러분께서는 자리를 지켜주시기 바랍니다. 그럼 지금부터 허준희 교수님의 기조 강연을 시작하겠습니다. 이번 기조 강연의 좌장이신 포항공대 수학과 이경석 교수님을 연단위로 모시겠습니다. 박수.
네. 네. 네, 허준희 교수님 강연을 시작하겠습니다. 일단 소개는 물론 이제 소개가 필요 없는 분이지만 제가 영어로 하겠습니다. So it's my great pleasure to introduce Professor Junhee Ho from Princeton University and KIOS. So he doesn't, as everyone knows, he doesn't need any introduction, but let me still introduce him. So he got his bachelor and master degree in Seoul National University in 2007 and 2009. And he got his PhD in University of Michigan in 2014. And he won many prizes and many honor. So most of all, he was invited to ICM in 2018, and he won first medal in 2022. And he will give the first plenary lecture for this meeting. And the title of his talk is A Decomposition Theorem for Lab Stats Module. So let's welcome him. Yeah.
Okay, it's my great honor and also a true pleasure to be able to speak here in this very, very important day. And I want to share my recent work with my friends and collaborators, Omid Amini and Matt Larson, titled The Decomposition Theorem for Lab-Test Modules. So I had great fun pursuing this topic with friends, and I want to share my enthusiasm about these objects and the properties they satisfy. And I hope the math in here is good enough to match the importance of the day. Okay, so I want to give a two-part talk where the first part is a historical survey of certain important development in algebraic geometry made during the last 100 years. And the second part talk happens to be our Vice Minister's favorite subject, linear algebra. And our results, the new results, will entirely lie on the second part. In particular, you will need not know any algebraic geometry or any other field of mathematics to understand and make sense of the main assertions that I'm going to show you later. And I'm giving the first part talk in order to motivate some of the statements that I'm going to show you in linear algebra. Because you might think that some of the statements that I'll show you is quite weird or even difficult, but this is only because you might not be familiar with some of the implications that I'm going to make. And these types of implications are heavily motivated by some of the foundational theorems discovered by algebraic geometers during the last century. So first part, the historical overview, and the second part on linear algebra. I should also mention a little bit of the applications of the main results that I'm going to share, but I do not wish to spend too much time on it. But let me just mention that the applications of the linear algebra statement include simple proofs of at least two results that were previously thought to be quite complicated. The first one being my work with another group of friends on Dowling-Wilson conjecture in combinatorics, which is something like a 17-step induction that spans across more than 100 pages of very dense paper that we spent like more than 7 years to complete. But assuming the linear algebra statement that I'm going to show you, there is essentially a half-page proof of this conjecture from the 70s in combinatorics. And actually, my experience in working with this other group of friends led us to consider this linear algebra statement that I'll show you later. Another previously thought difficult result that comes out very easily out of this linear algebra lemma is the existence of polarized pure Hodge structure on the intersection cohomology of a complex projective variety. So there will be no need to explain what is meant by that, but I'm going to briefly tell you what this intersection cohomology is. And it has been widely believed to be true that there exists this thing called the polarized pure Hodge structure on the intersection cohomology of any complex projective variety. And some of the leading mathematicians in the 80s have seriously thought about this, like Bailinson and Deligne and so on, McPherson. But it was not clear, at least to them, until the Morihiko Saito came up with his theory of Hodge modules to settle this thing. But the Saito's work is generally considered to be extremely involved, and our linear algebra lemma at least partially lets us avoid the full development of the theory of Hodge modules to reach this conclusion. But let me emphasize that this linear algebra lemma is really a lemma, and in the end, it's something that you can confidently explain to the maybe one or two best students in your linear algebra class. It's just the implication that a certain explicit matrix defined in a certain way, if that is positive definite, then you can also show that some other explicit matrix that you can define in some other way is also positive definite. And that implies everything else that I'm going to show you in this paper. So part one, algebraic geometry. So I want to start with the tale of Solomon Lefschetz, who recorded in his autobiography saying this rather famous sentence: "As I see it at last, it was my lot to plant the harpoon of algebraic topology into the body of the whale of algebraic geometry." So harpoon is a chaksal, so the thing that you put inside in the whales until it was forbidden to do so. But anyway, so this is what he said about his own work in his later years. I imagine it would be a very happy person to say something like this for his own work. And one of the things he was referring to is this statement called the Hart-Lefschetz theorem. So here, X is a d-dimensional smooth projective variety over C, and L is a hyperplane class in its cohomology. And it's a certain statement that the cohomology groups in complementary dimensions are isomorphic in this particular way. You just multiply the cohomology class of the hyperplane right number of times until it lands in the complementary dimension. And this is the statement now believed to be fundamental, called the Hart-Lefschetz theorem. Of course, Lefschetz did not call it that way, and it looks like Grothendieck was the one who coined the term, and is in particular calling it Hart. The French name is Theorem de Lefschetz-Vache. I don't exactly know the kind of a connotation to the last expression, which means cow in French, but also a kind of a slang. So maybe the more literal translation would be a theorem that's freaking hard, or something like that. And then the English translators like milded it and called it the Hart-Lefschetz theorem, and now everybody calls it Hart-Lefschetz theorem. And I'm going to call this HL. So it's a rather strange statement. Since Poincaré, who was also already mentioned, people knew that the cohomology and complementary dimensions are dual to each other, but this is not that statement. This is the statement that the two vector spaces, which are dual to each other, are also isomorphic to each other. Okay. So it is generally believed that the Lefschetz never proved the Hart-Lefschetz theorem. So he had an argument that was never completed, and the fully rigorous proof had to wait at least 20 years, this was 20s, until Hodge developed his theory of harmonic forms. This is 40s. So these are the two interesting quotes that I found about Hodge's work in the 40s. Whitehead said that I would have sold my soul to the devil for such a theorem. I'll show you some of his theorems. And Atiyah, in his obituary to Hodge, says that the proof was, in his own words, crude in the extreme. And remember, this was developed partially in order to justify the Hart-Lefschetz theorem, which had no justifiable proof. But the Hodge's proof, which was supposed to salvage that part, among other things, also had bumpy parts. So Hermann Weyl found it hard to judge whether the proof was complete, or rather how much effort would be needed to make it complete. Okay. So through the work of Hodge and later contributions by Weyl and people like Kodaira, who finally settled and smoothed out the rough patches, and we arrive at conclusions like this. So maybe you have seen this famous formula which says that the kth cohomology of a d-dimensional smooth projective variety has the so-called Hodge decomposition into PQ parts. So HPQ is the cohomology classes of the PQ forms, closed PQ forms, and this is a direct sum decomposition. A lesser known consequence of the theory of Hodge of harmonic forms is the following. It's a rather lengthy statement, and this is the part that concerns the funny linear algebra statement. So, for example, let's look at the self-pairing on the PP part of the cohomology of X. What I'm going to do is I take two PP forms, both closed, and then I'm going to wedge them, taking one of them with a complex conjugate, and then multiply by the hyperplane class L, right number of times, so that the whole expression becomes a top class. And I integrate over X and put the right sign, which is -1 to the P. And then the statement is that this pairing is positive definite, not on the whole space, but on the kernel of L to the d minus 2p plus 1. So L to the d minus 2p is the power that appears in the Hart-Lefschetz theorem. And you go one more step, and then the Hart-Lefschetz map will be no longer an isomorphism, but it will create a kernel. And the statement is that the pairing is positive definite on that kernel. So now the kernel, we usually call it the primitive part of the PP cohomology of X. And this is one of the statements that Hodge stumbled upon that extends the more classical statement of Riemann on H10 of our algebraic curve, or Hodge's own statement on H11 of algebraic surfaces. So let's keep this structure of the statement in mind for later. And let's move on to 50s. So here, Chern and Wei smoothed out and found many of the very beautiful, but at the moment unfamiliar algebraic structure that goes behind the Hart-Lefschetz theorem and the Hodge-Riemann relations. And that one of the observations is that Hodge has this star operator that defines the degree lowering dual operator of L. And the triple L and L star and their commutator form SL2 triple. So SL2 is the one of the most fundamental Lie algebras. And in the cohomology, you see its representation. So this is a simple Lie algebra, which implies that the cohomology of a smooth projective variety can be written as a direct sum of simple SL2 modules. And we understand all the simple SL2 modules. So we know that the cohomology has a rather simple explicit description. And this is called the Lipschitz decomposition. So the linear algebra result that I'm going to show you later can be viewed as an extension of this statement. So this is my cartoon picture of a cohomology or even part of the cohomology of a projective variety. So each box corresponds to the one-dimensional vector space, and the height of the boxes corresponds to which cohomological degree it lies on, and the right-hand side shows the Lipschitz decomposition. And each string of boxes corresponds to simple SL2 modules. And here, the decomposition into simple modules is not unique, but if you group all the modules so that the isomorphic modules are grouped together, then this gives the so-called isotypic decomposition, which is unique. And as it is a rather simple picture, but this only captures a very small part of the relevant algebra because you have the freedom to vary L. Remember, L comes from one particular chosen hyperplane class, but a given projective variety can be embedded in projective spaces in so many different ways, and each way gives its own hyperplane class. So in a sense, you have a varying structure of SL2 module decomposition as you vary your L. And the next big result happened in the 70s by Goreski and McPherson, where they introduced the intersection cohomology. So intersection cohomology is equal to cohomology when the space is smooth, but not in general. And here I found this funky quote from Stephen Kleiman's survey on intersection cohomology. This is what happened when Goreski and McPherson presented their new and better definition of cohomology and presented it to topologists in the 80s, maybe. And this was at the height of algebraic topology. And people have been working with cohomology for hundreds of years, and you don't want to mess up with the definition of cohomology. And this is one of the typical responses at that time. But it turned out that the new definition is really the better definition. So one of the main outcomes of the so-called intersection cohomology theory is that for any projective variety X over C, notice that I no longer require X to be smooth. There is an HX module IHX. So cohomology is a ring, but intersection cohomology is not a ring, but a module over the cohomology ring. And this new module satisfies Poincare duality. The cohomology ring does not, unless X is smooth and compact. And this IH satisfies Poincare duality no matter what. So their main motivation was to fix this failure of Poincare duality. So our great Poincare have noticed that smoothness implies duality, but Goreski and McPherson noticed that actually that is true no matter how singular your space is. And not only that, Goreski and McPherson and other mathematicians at the time almost immediately realized that conjecturally this new and better definition of cohomology IH should satisfy also something called the decomposition theorem and the Hart-Lipschitz theorem that I have shown you before, and also the Hodge decomposition that we talked about, and also the Hodge-Riemann relations. So these were the central conjectures at that time, and shortly after, the first two parts, decomposition theorem and the Hart-Lipschitz theorem, was settled by a very influential paper of Bailinson, Bernstein, Delin, and Gabor on perverse sheaves. And the latter two parts had to wait a little more until Saito developed his theory of Hodge modules. Okay, so I want to remind you that you can very casually filter through all this information. So I'm not trying to explain every detail. I just want to make you motivated or make you ready to observe the linear algebra statement that will come in part 2. And I promise you that the part 2 will be entirely linear algebra. That has nothing to do with any of these fancy stuffs. Okay. So this is the influential paper BBDG on 1982 called perverse sheaves, which proves, among other things, hard Lefschetz for IH. So so these days, thanks to our AIs, it's very, very easy to find and verify interesting quotes to share in the talk like this. And this is the one that I like the most. So this is, there's a huge volume of Grothendieck-Serre correspondence, collecting all the papers from Grothendieck and Serre and vice versa. And this is one of the last entries and probably the most famous letter because gossip-loving nature of mathematicians, because this is the letter or the response to a letter where Grothendieck trashes Delin's work and Serre tries to defend Delin's work. But there are some other parts to that same paper. So Grothendieck stopped writing to Serre for 15 years, and then suddenly he sends a letter to Serre. And what does he write about? He complains about the recently introduced definition of perverse sheaves. Not the mathematical definition, but the choice of the words. So perverse sheaves is famously known to be not perverse, and secondly, not a sheaf. So very few people like the name at the moment, but this is what we're stuck with. And now many people love it. So I dislike the term perverse just as much as you do. That's one point we agree on. So there were a couple of other points they did not agree on intensely. Okay. So one of the things that the theory of perverse sheaves gives you is the Hart-Lefschetz theorem for the intersection cohomology. Another theorem that it gives you is this thing called the decomposition theorem. So this is the statement at the level of intersection cohomology. So for any map of, let's say, projective varieties x to y, without any assumption on the singularities, you can decompose the intersection cohomology of x as a hy module. So hy pulls back to hx, but ih of x is a hx module, therefore hy module as well. And you can decompose it as a hy module. And the main conclusion is that the summands you see in such a decomposition are also intersection cohomology of certain spaces. One caveat is that you have to introduce the local coefficients, L alpha, but that does not concern us here. But the interesting part is that maybe this is one of the first instances where a big theorem of complex projective varieties was proved by reducing the statement to the case over finite fields. And not just characteristic P, they needed it to be over finite field. And because of this reduction to the finite fields, they had to use the étale cohomology. And for technical reasons, they had to use L-adic coefficients for their étale cohomology, which prevented them from approaching the Hodge-Riemann relations. Remember that funky statement which says that something is positive definite? You cannot even make sense of that statement if you are working with cohomology theory with L-adic coefficients, because there are no negatives and no positives in L-adic numbers. So they just proved Hart-Lefschetz, and they couldn't touch the Hodge-Riemann relations. So this is quote from influential survey on decomposition theorem by Di Cataldo and Migliorini. You might find this very mysterious if I just give you this, but it is generally considered that the decomposition theorem is the deepest known fact concerning the topology of complex algebraic varieties. And many people agree. So I love their decision to state it in this way and not saying that it is like one of the deepest statements in algebra. I mean, people always say it's one of the best theorems, but then that doesn't mean anything. Right? They are very clear on what they consider to be the deepest known fact on topology of complex algebraic varieties. But it's interesting that that deepest fact on topology is proved using the reduction to the finite fields. Okay, so for the Hodge-Riemann relations, saying that something is positive definite, we had to wait until Morihiko Saito developed his theory of Hodge modules. So among other things, this theory gives the Hodge decomposition and the Hodge-Riemann relations for the intersection cohomology, valid for any projective variety over complex numbers. So this part is one of the things our linear algebra lemma recovers. And this is support to my claim that this is a difficult theory. So in their textbook to mixed Hodge structures, they say that many mathematicians consider Saito's formidable work to be rather impenetrable. But this was a long time ago, so and many young researchers now casually use mixed Hodge modules and Riemann-Hilbert correspondence and like that, but it is still a difficult theory, it looked like to me. Okay, now we forget everything. So everything you heard so far is irrelevant. And then I'll show you the linear algebra implication that I find very, very miraculous. So I'll need a little bit of setup time to introduce the statement, but I think it will worth 5 minutes of your attention. So this is a statement about 4 objects interplaying with each other in particular way. So these 4 objects will be A and M and KA and QM. I'll introduce them in order. So A is a finite dimensional commutative graded algebra over the real numbers. And M is a finite dimensional graded A module. So A acts on M. In my mind, A is like a cohomology, and M is like an intersection cohomology. The real player will be this KA. This is a subset of the degree 1 part of A, and it will be a non-empty open convex cone. So notice that I use the word convex. So I'm really doing linear algebra over the real numbers and not over any other field. This convexity is very important for me. And it should be also open, which means that in particular it's full dimensional. The last object is QM. This is a symmetric bilinear pairing of M with values in R, with the property that the pairing of AX and Y is same as the pairing of X and AY for every A and every XY in M. So I'm going to refer to this as a QM is A invariant. So in my mind, QM will be the Poincare pairing defined on the intersection cohomology. But we don't have to stick to that setup. And this is a definition. This is the assumption to which I'm going to apply my theorem to. I'm going to say that M and QM is a Lefschetz module of degree D over A, KA. If Poincare duality is true, Hart-Lefschetz theorem is true, and the Hodge-Riemann relation is true. And the statement is exactly as you have seen before in the setting of geometry. So Poincare duality, QM is non-degenerate, and Hart-Lefschetz says that for every K, at most D half, and every choice of L chosen inside from this open convex cone K, you have an isomorphism between the complementary degrees obtained by multiplying L right number of times. So this is a varying family of isomorphisms. where you vary over a convex cone. And the third is that if you pair an element to its Lefschetz dual pair, put the right sign in front of it, and then the statement is that this should be positive definite on the kernel of L to the D minus 2k plus 1. It's such a weird statement, but it's a definition, and we have the freedom to define whatever things that we want, so long as it has interesting consequences. So actually, it's a completely irrelevant side remark, but in the near or distant future where we develop an AI system from scratch, like the ones that have never seen humans doing mathematics in whatever way, I'm rather curious, I'm not really interested whether they will be able to prove the Hart-Lefschetz or Hodge-Riemann relations. I'm more curious whether they will have this burning desire to want to prove these weird statements, because it's generally agreed among algebraic geometers that these three properties are essential properties to understand if you want to understand the theory of motifs, for example, and which in turn explains almost every other cohomological phenomenon. But as it stands, it's a linear algebra statement of very, very peculiar nature. So, but as we have discussed, these weird structures do exist, and they exist in abundance for some reason. So I've already told you that if you, extending Hodge's theory a little bit further from projective case, X is a compact Kähler manifold, and if I take the real part of the KK cohomology and take Ka to be the Kähler cone consisting of all Kähler classes, and Qm be given by the cup product, then this is a Lefschetz module. That's the summary of this first 50 years of development I've shown you before. And also, and this is Grothendieck's standard conjectures. And the reason why Grothendieck was so mad at Deligne was that Deligne proved the Weil conjectures without proving Grothendieck's standard conjectures, so bypassing his theory of motifs. Supposedly, if you take any smooth projective variety over algebraically closed field and take the child group modulo numerical equivalence so that the Poincare duality is built in, and take Ka to be the ample cone and Qm to be the pairing given by the intersection product, then this is conjecturally a Lefschetz module. And if you can prove this, you can prove wave conjectures and other things. But more recently, mathematicians have been discovering new Lefschetz modules in surprisingly diverse contexts that have, at least from outside, has nothing to do with each other. This is a miracle. So people have discovered that what you call the IH of a convex polytope, which is defined in a completely different way, and take the strictly convex PL functions as its cone, then this is a Lefschetz module. That's the theorem of Caroux. And in a completely different context, if you take a Coxeter group element and take the so-called reduced Sorgel bimodule associated to it, and take K to be the open dominant cone, that this also has the structure of a Lefschetz module. And my work with other friends are saying that the Chow ring of a matroid, this is a combinatorially defined object, and take the cone of submodular functions on the ground set, and this is a Lefschetz module. And we have recently discovered a few others, which is provably not of the kind 1 or 2 or 3 or 4 or 5. So there are many, many Lefschetz modules that appears in nature. And each of the numbered families have very small intersection with each other. So Lefschetz modules exist in nature. We don't know why, but they do exist. I want to show the properties that they have, and that will be our linear algebra lemmas. So this is the setup for the theorem. So let's say M is a Lefschetz A module as above, and I'm going to choose B, and B will be any subalgebra of A generated by any subset of the closure of this cone Ka inside A1. Notice that I'm taking the closure, and I have the freedom to choose any subset from closure. And I'm going to define a new open convex cone KB inside B1. So this will be the interior of the closure of Ka intersected with B1. So this is a face of the closure of Ka. So usually much, much smaller than Ka. So in my mind, this B being a subring of A replaces the arrow in algebraic geometry, which is a morphism from X to Y. Remember, A is like the cohomology of X, and B is like a cohomology of Y. And the only requirement is that B is generated by a limit of positive elements. And then I want to prove the decomposition theorem. So I choose any decomposition of M into indecomposable graded B modules. So there's no content in here. It's clear that such a decomposition exists because everything is finite dimensional. The only thing is that the decomposition need not be unique. But the familiar Kroll-Schmidt theorem applies in this context, which tells you that decomposition is in some sense unique up to isomorphism. You can pair the summands, indecomposable summands, in two different decompositions bijectively so that the corresponding pairs are isomorphic as graded B modules. So once we fix any decomposition, I can write the decomposition as a sum over alpha and k, where n alpha are indecomposable graded B modules, and n alpha and n beta are not isomorphic as graded B modules for different alpha and beta. And each n alpha ranges from degree 0 to a certain degree, d alpha, where in degree 0 it's non-zero and in degree d alpha it's non-zero. We can always index things like that. So this is how I'm indexing stuffs. So imagine I have a graded module M, which is an A module. And perhaps as an A module, it's indecomposable. But I'm choosing a smaller ring, B, and this A module will decompose further. And I'm just going to collect which indecomposable summands are isomorphic to each other up to a shift. If they are isomorphic up to a shift, I label by same alpha. So here's my n alpha. If I see another isomorphic object, I put it here, n alpha shifted by degree 1. And here I see a new indecomposable summand, not isomorphic to the ones that appeared before. I call it n beta. And here I see another non-isomorphic summand. It's concentrated in a single degree, so I call it n gamma. I see the same thing in a different degree. I call it n gamma minus 1. I see another thing. I call it n gamma minus 2. So far, nothing happened. You can always write things like this. And the main conclusions of the theorem is that if you start with the Lefschetz module M, then the shape of the resulting Kroll-Schmidt decomposition should be extremely specific. And that will be the statement of the theorem. So it will be a many-part theorem, and I'll go over one by one. So the first part, for the lack of a better word, we call it the shadow of simplicity. So take any alpha. So choose n alpha. Remember that n alpha could be any one of the indecomposable B modules that appears in the decomposition of M. Choose one of them. And of course, you cannot hope for this B module to be simple, because graded B modules are never simple, basically. If you have a graded module over a commutative ring, you can always quotient out by a positive degree elements or part degree larger than 3, and this is always an ideal. And therefore not simple. But these graded B modules behave as if it were simple. For example, we have this miraculous property that if you look at the endomorphisms of N alpha as graded B module, you have only three possibilities. One is R, which means that the only way to map a N alpha to N alpha homomorphically as a B module is just to multiply by a real number. This is the most obvious case. But there are two other cases, only two other cases only. Two other cases being that the endomorphism ring being isomorphic to C, and another thing being isomorphic to H, the quaternions. So, I recently watched this project Hail Mary, and there's a little part that the main character tries to communicate or build up a way to communicate with his alien friend, and then he discovers that they have a somewhat limited shared mathematics. And this is, hypothetically, something like this could happen. So remember that everything we have done so far was entirely over the real numbers. I've never mentioned anything complex, anything quaternions. This just came out of nowhere. So if there's an alien species who likes real numbers, but have never ever thought about complex numbers or quaternions, this is the way hypothetically they could discover them, right? They would realize that in order to understand the category of motives, it's essential to understand Hart-Lefschetz and Hodge-Riemann, and therefore end up in this kind of a theory of the decomposition of Lefschetz modules, and realize that there are only three possibilities for the endomorphisms of the indecomposable objects, and just define them as complex and quaternions. And maybe later, maybe 100 years later, they will discover that these endomorphism rings have applications in understanding quantum physics and other things. Right? And they also have a similar characteristic to the simple things, simple modules in some abelian category. And basically, the statement is that you never have a homomorphism from an object to an object that lives higher. So if the middle degree of N alpha is at most the middle degree of N beta minus K, then there are no non-zero homomorphisms between them. So that's the first part. And for those of you who know, this is supposed to be the shadow or linear algebra counterpart of the statement that the simple object in the category of perverse sheaves on a complex projective varieties are IHs. Those summands that appear as a summand in the decomposition theorem of Bellin-Bernstein, Deligne-Gabbard. Okay. The second statement is as follows. So for each alpha, any one of the summands N alpha is self-dual up to a shift. So N alpha is isomorphic to N alpha dual shifted by minus D alpha as graded B modules. So this is the statement that if you start with a Lefschetz module and decompose it, then each one of the summands has its own Poincare duality, which is not in any obvious way related to the Poincare duality pairing of the ambient M. So this statement is that up to a non-zero real multiple, there is a unique non-zero B invariant symmetric bilinear form that pairs N alpha with N alpha, where the non-complementary pairs are orthogonal and complementary pairs non-degenerately. So this Q alpha being non-degenerate is the statement corresponding to Poincare duality. So this is actually a rather subtle statement because N alpha being isomorphic to its dual. If you remember the earlier statement on the endomorphism ring, the way it can be isomorphic to something that is isomorphic to is one of the three ways. It could be isomorphic the non-uniqueness is either R or non-zeros in R or non-zeros in C or non-zeros in H. So it looks like for the pairing, which is almost the same thing as a homomorphism from N alpha to its dual, you also have three possibilities, R or C or H. But the statement here is that there is a unique up to a non-zero real multiple. So what happened to this cases C and H? So the point is that even on those cases, if you require the pairing to be symmetric, there is a unique pairing, unique symmetric pairing among those complex or quaternionic worth of bilinear pairings. So that's Poincare duality. And the third is Hart-Lefschetz. So each summand has its own Hart-Lefschetz. And the point is that, first of all, the degree bound is of course different. K should be at most D alpha over half. And the Lefschetz operator L now varies inside KB. So remember, KB is a face of the closure of KA. Of course, if you have a Hart-Lefschetz operator on M, and it varies inside this open convex cone KA, well, Hart-Lefschetz is a statement that some vector space is isomorphic to some other vector space by this matrix. And as you take the limit of your matrix to the boundary, there is no guarantee that, and in general it will be almost never true, that in the limit it will stay an isomorphism. Because in the limit, the kernel will be created. But here, the statement on L varying on Ka is replaced by the statement L varying on Kb. And it's the isomorphism on each summand. And the fourth part is the Hodge-Riemann, which looks almost exactly the same, except that there is an ambiguity about the sign that only depends on alpha. So you can find the consistent sign so that each N alpha satisfies the Hodge-Riemann relations in almost exactly the same way. Again, with the same caveat that the L should now vary on this cone KB. Of course, we are talking about B modules rather than A modules now. In short, if you start with the Lefschetz A module M and decompose it as a sum of indecomposable B modules, and maybe call it one of the summands to be N alpha, then N alpha will be, in a natural way, a Lefschetz B module. So it almost behaves as if something like the category of Lefschetz modules decomposing within itself, except that you have to change the rings, change the cones, change the pairings, and so on. So this is my cartoon for what happens in general. So this guy, this chunk of green boxes, was my cartoon for M. And in degree 0, dimension was 3, degree 1, dimension was 4, and degree 2, dimension was 3. And as I vary my L inside the cone K of A, degree 0 part will be isomorphic to degree 2 part. That is Hart-Lefschetz. But if I take my L to be at the boundary so that L is now inside K of a B, then multiplying by L twice will no longer be an isomorphism between degree 0 and degree 2. So it will, let's say it has a two-dimensional kernel, which are the two red boxes, kernel of L squared in degree 0. And the statement is that if you decompose your M as indecomposable B modules, as we have did before, then the red boxes go here and here. And within each summand, there is no contradiction to the Hart-Lefschetz with respect to the cone of B. So the Hart-Lefschetz here is a statement that multiplying by L once is an isomorphism. Of course, if you multiply twice, then it will go to 0, as was explained before. But that is not a contradiction to hard latches within the summand, because the d alpha have changed. And same for here. There's no statement for hard latches there. Okay, so the fifth part is this hidden structure called the perverse filtration. And the statement, to put it bluntly, is that the perverse filtration defined by the shown equality is canonical. So canonical is a heavily overused word, but this, in this context, is what I mean. Remember that the right-hand side depends on the chosen decomposition of M. So the Kroll-Schmidt decomposition, remember, in general, is highly non-unique. But I'm saying that if you sum the summands in this particular way, d alpha plus 2k is at most j, then the sum of those summands do not depend on the chosen Kroll-Schmidt decomposition of M. This is something completely canonical about the B module structure of M. And this is the cartoon picture for it. So take the same A module M, look at it as a B module. Now I'm going to arrange the summands in a different order so that the middle degrees of each summand is gradually increasing. So this is the first part, P0. This is the second part, P1. You sum the two. This is the third part, P2. You sum the first four summands. This is P3, and that is P4. And each Pi is a B submodule of M that does not depend on anything. This is just something M knows secretly. Since you have a filtration, you have the associated graded module. But your original M was a graded module, but you have an extra filtration so that now your associated graded is bi-graded with I and J. So I was the original grading, and J is coming from this perverse filtration. It's the perverse degree. And the statement is that this associated graded has a unique isotypic decomposition. This is one of the subtle things that happens within the context of decomposition theorem. So M and its associated graded are isomorphic as B modules. So it looks as if we have not done anything. At least B modules are concerned. And we already know that the B module decomposition of M is highly non-unique. So it looks like there's nothing unique. But if you take account into this canonical perverse filtration and try to decompose associated graded with the perversity J fixed, then that graded piece of GR has a unique canonical decomposition into indecomposable B modules if you group the isomorphic ones together. So this is very, very similar to what happens to the, let's say, theory of representations of a simple Lie algebra. If you group the isomorphic submodules together, then that becomes a summand. So there's a whole machinery that goes behind showing that some category is semi-simple. This is actually a strengthening of this thing called the Lepsch's decomposition. Remember what Chern and Wei did for one single L chosen from the interior of Ka, where everything was a SL2 module and therefore has a unique isotypic decomposition. So in that case, my B was generated by a single element chosen not in the boundary but from the interior of a Ka. Then it just so happens that the perverse filtration will be trivial, because if you remember the cartoon before, in that case, the centers of all the summands are aligned. which means that the perverse filtration will be 0 until the middle, and then will stay everything as M after the middle. So this unique isotypic decomposition will reduce to the isotypic decomposition of SL2 module in this case. So that was the fifth statement. I have one more statement concerning the associated graded. So it's not hard to check that this perverse filtration has the property that if you multiply by any degree k element in A, then Pj goes to Pj plus 2k. It's a direct computation. Therefore, this GR has an A module structure where multiplying by degree k elements raises the degree by k in the first factor and by 2k on the perverse degree. And the sixth statement is the so-called the relative Hart-Lefschetz statement. So I'm going to consider a third cone. Remember, I had the cone Ka and the cone Kb, which is the boundary, and this is the relative cone. This is simply the sum of Ka and the degree 1 part of B. And the statement is that for every j at most d and every eta chosen from this relative cone, we have an isomorphism between the complementary degree pieces of the associated graded, given by that A module structure. So this is a certain linear algebra statement that implies, among other things, that for each alpha, the multiplicities M alpha k is symmetric and unimodal sequence in K. So remember that M alpha k remembers how many times N alpha appears starting from degree K. And the relative Hart-Lefschetz says that the distribution of the sum n's isomorphic to N alpha up to a shift cannot be arbitrary. If you see N alpha twice in degree 2, you should see N alpha exactly twice in co-degree 2. For example, so the Kroll-Schmidt decomposition, on the surface of it, it looks like it could be completely arbitrary, but they have all these hidden symmetries. So this is the summarizing cartoon picture for the decomposition of the Lefschetz module. And this combination of this whole package is what I call as a miraculous lemma that has many implications. And the final picture that I want to explain is this one. So I start with the Lefschetz module M. This is an A module that has Hart-Lefschetz and Hodge-Riemann and Poincare duality. That's it. Now I choose a smaller ring B generated by subset of the closure of this cone K. And it will be decomposed into indecomposable pieces. And then I'm going to write the sum n's in this particular way so that they reflect the perverse filtration. So middle degrees are increasing as I go from left to right. I take the associated graded so that the sum n's represents the homogeneous degree components. And for the sake of aesthetics, let me shift the degrees of each one of the homogeneous degree components of the GR so that they have the aligned middle degree. And then the whole picture summarizes most of the conclusions that we have seen before. So first of all, if I take L from the cone K of a B, then each sum end has a Hart-Lefschetz going upwards. So this purple thing has a Hart-Lefschetz by multiplying L once, and this middle one has a Hart-Lefschetz from degree 0 to degree 2 by multiplying L twice. But also, there is a horizontal Hart-Lefschetz. This is a relative Hart-Lefschetz theorem. And the statement is that if you choose any eta from this relative cone K of A over B and apply this funny A module structure on the associated graded, then you have the horizontal Hart-Lefschetz. So it goes from here to here, and that's an isomorphism of vector spaces, or go from here to the red box by multiplying eta squared, and that is another horizontal Hartleb-Schutz. So maybe the most classical example where you see this kind of structure is indeed from the geometry. If you have a projective variety from x to y, a map up from x to y, then you will have a picture like this. And I have omitted this part for the simplicity, but actually everything you see, if you start with something with a Hodge structure, will be a morphism of Hodge structures. So you should think this really as a three-dimensional array of boxes where each one of the squares has a Hodge decomposition. So imagine Hodge decomposition of this box. List another boxes in this three-dimensional array as its PQ parts. And then each PQ parts will have its own complex conjugate symmetry. So this x-axis corresponds to the relative Hartleb-Schutz. The z-axis corresponds to Hartleb-Schutz for each one of the summands with respect to the ample cone of the base. And there is this y-axis that displays the Hodge decomposition of each one of the squares. So I did not appreciate this picture a lot, but I mean, geometers tend to think of a given smooth projective variety in terms of its Hodge diamond. So it has like this, it's a diamond. So the entries are PQ parts of the cohomology of X, and people usually imagine this as the Hodge, call it the Hodge diamond of X. But actually what happens is that if you have a map of projective varieties from X to Y without any assumption on the singularities, you should really think of it as the Hodge octahedron. So you have this Hartleb-Schutz of the base, Hartleb-Schutz of the fibers, and the Hodge decomposition of each one of the parts, primitive parts. And this gives you a way to visualize the Hodge theoretic informations in the numerical way. And for some amazing linear algebra reason, they always comes to us in this highly, highly structured way. Oh, and if you apply this linear algebra to different contexts that I showed you, in the context of polytopes, context of Coxer groups, context of matroids, every time different things pop up, and that was a great joy to witness. So I'll stop here and thank you for listening.
Thank you very much for the great talk. And is there any question or comment? Since we are running out, please, yeah. Let me. 네.
강연 잘 들었습니다. 그 여쭤보고 싶은 게 있는데요. 그러니까 아까 전에 그 말씀하시기로는 그 여러 가지 분야에서 코호몰로지와 그에 관한 스트럭처들이 나온다고 하셨잖아요. 그런데 대수위상수학이나 아니면 대수기하에서는 코호몰로지 말고 또 다른 중요한 오브젝트로 펀디멘탈 그룹이 있단 말이에요. 그리고 이 둘은 사실 굉장히 관련이 있는 오브젝트예요. 혹시 펀디멘탈 그룹도 여러 가지 객체에서 비슷하게 나타나나요?
네, 뭐 non-abelian Hodge theory를 열심히 연구하시는 분들이 있죠. 제가 어렴풋이 이해하기로는 정확히 그런 목적을 가지고 연구하는 분야라고 알고 있습니다. 네, non-abelian Hodge theory에 대해서 읽어보시면 거기서부터 시작일 것 같아요.
감사합니다.
Any further question or comment? Yeah, since is there any? Yeah, please.
Yeah, thank you. So I think you didn't say much about the proof of the linear algebra effect. So is it the proof goes on like a standard way, or do you use how do you? Could you say something about the proof?
So this is I think one should agree that this is fundamentally a linear algebra implications. because there's no variety, no polytopes, no nothing. It's just linear algebra data, and I want to deduce this conclusion. So proof must be some kind of very tricky linear algebra. It was very tricky for us, and we have struggled for many months.
Okay, maybe one last question? No? So can I ask you one question? So is there any, can I restate this in terms of corresponding ring over B? Or you say that when A and B has B decomposition, then it seems that your theorem can be also restated in terms of corresponding ring of variety, decomposed corresponding variety in terms of corresponding variety of corresponding ring over B. Is it possible?
Yeah, the main statement is a linear algebra implication. So whenever you have a Lefschetz module, any reasonable decomposition will produce new Lefschetz modules. So for example, if you're in a case where you're lucky enough to prove Grothendieck standard conjectures on algebraic cycles, then it strongly suggests that there should be actually a stronger conjecture that resembles exactly the same statement without the smoothness assumption. So there should be something like the Chow version of intersection cohomology with Q coefficients, and those also necessarily satisfy the standard conjectures or strengthenings of standard conjectures. But according to the lemma, presumably the more general conjecture can be reduced to the case of smooth varieties if you know resolution of singularities exist.
Okay. Thank you. So yeah, let's thanks to Professor Ho again for his great talk. Yeah. Thank you.
이 중의실 1하고 2를 지금 개방을 했는데 원복을 하기가